What's up, everybody? Welcome to lecture 17. It's all over section 3.2. We're going to start off with this definition, Rolle's theorem, or rather this theorem, I should say, not definition. We're going to start off with Rolle's theorem, which states that if each of these three conditions are true, then we can say that there's a c inside of a particular interval such that the derivative of our function is going to be equal to 0. Now, let me actually state what all that says. So what Rolle's theorem is telling us is if we have a function that is continuous on a closed interval from a to b, the function is differentiable on an open interval from a to b. I'm going to come back to the reason for closed versus open here in a minute. And if this third condition, that f at a is equal to f at b, then there exists a c somewhere inside of this interval from a to b such that the derivative of your function at that c is equal to 0. Now, coming back to this idea of a closed interval versus an open interval. To explain the reason for this, why it's important to note that one is closed, one is open, all we need to do is go back to the definition of the limit. The actual thorough, deep definition that we had talked about in, what is that, chapter 2, I think? No, chapter 1. The reason why we have this being closed and this being open is that to take a derivative, you need to be able to apply the limit, right? Which means you need to get to values from the left and from the right. Well, if you had this being closed, you can't get to A from the left and you can't get to B from the right. So this second definition being open is a result of our application of the limit. That said, the first part of this theorem being closed is just that we could talk about continuity on a closed interval. So I just wanted to make that distinction there. Having said all that, let's check out an example. All right, so let's consider this example here. We want to prove that x cubed plus x minus 1 equal to 0 has only one solution. How are we going to do that? Well, if we consider what we know that if we consider f of x to be equal to x cubed plus x minus 1, then this function at 0 is equal to negative 1. At 1, this function is equal to 1, and the derivative of this thing is equal to 3x squared plus 1. All right. How are we going to use all of this? Well, for the first part, we're just going to focus in on these two things right here. Because our function is continuous, and f at 0 is equal to negative 1, and f at 1 is equal to 1, then by the intermediate value theorem, tells us that there must be at least one value c let's call this value C, yeah. One value C, and it's going to be between 0 and 1, such that our function at C is equal to 0. So we've just proven that there's at least one solution to this problem. Now we need to prove that there's only one. So we've proven that at least one exists. And we did that because we observed, one, this thing's a polynomial, so it's always continuous. And two, our function at 0 is equal to -1, and our function at 1 is equal to 1. So by the intermediate value theorem, it's got to be the case that there's at least one value in between 0 and 1 that our function passes through 0 at. Okay? So what now? How are we going to prove the other part? So we've proven that there's at least one value. Now we need to prove there's only one value. Well, now we come over here, we say, our function is equal to x cubed plus x minus 1, but its derivative is equal to 3x squared plus 1. And this derivative is always greater than or equal to 1. So what that means then is that this thing can't dilly-dally back and forth, right? It doesn't go up and down. It just is always increasing. That's what this is telling us, because the derivative is always greater than or equal to 1. So it never stops increasing. We don't have a flat spot. It's only ever going to increase. Well, if that's the case, then once we pass 0, we'll never come back down. In other words, once our function passes through 0, it just doesn't come back down. So this tells us then that not only is there at least one solution, there has to be only one solution, because once you go past that solution, you don't come back down. So think about that graphically, what that means. And think about what that intuition, what the math is trying to intuitively tell us. Having said that, this observation is an application of roles, right? Because we're saying, all right, we know our function is continuous. We know that our function is differentiable, but at no point does our function equal to 0. Or, I mean, is our derivative equal to 0? So we don't finish that third condition, or that final statement. So we can then say that third condition isn't real. It doesn't happen. So take some time and think about this. There's some deep ideas, deep concepts here. And just a different way of thinking. Like, this problem has to be addressed in kind of a forward and backward direction, right? You have to attack it from the front end and from the back end. So you have to assume, using Rolle's theorem, that you have two solutions. And then you have to use that to prove that it doesn't have two solutions. And you have to prove that it has at least one solution. So there's a lot of things going on, a lot of complexity to this idea, actually. So like I said, take some time to really look over this problem and to think about it. There's a lot going on the back end. A lot of deep meaning, a lot of good, just problem solving. For those of you who are computer science students, this is actually the sort of thinking that you're going to have to apply a lot when working with different types of code. A lot of coding problems require you to figure out how you're going to build your objects, which means you need to figure out how you're going to build your class, the methods, everything that it has as attributes, all the inheritance properties, and then how are you going to actually implement them, and how do these other classes interact with each other? Do they inherit properties from each other? It's this type of problem that you're going to be working with as a computer science student a lot, especially if you get into OOP. For those who are not familiar with the jargon, that's object-oriented programming. That said, let's get on with the next theorem, which I believe is the mean value theorem. So this next theorem is called the mean value theorem. And it really only has two conditions, the same exact two conditions that were in the first two conditions of Rolle's theorem. That is to say that if f is continuous on a closed interval from a to b, and f is differentiable on an open interval from a to b, those are your only two conditions here. And if both of those conditions are met, then there exists a c in the open interval from a to b such that the derivative of your function at that c is equal to the quantity f at b minus f at a divided by b minus a. All right. What? Well, all this is really saying is that if you have a function that's continuous on a closed interval and differentiable on a closed interval, then somewhere inside of that interval, there's a value such that the derivative of your function at that value is equal to the average slope. Makes sense, actually, when you think about it, right? We're just saying that there's a line parallel. So let me draw it on the board. I think it'll be easier to see that way. We're just saying that we've got a function, maybe it looks something like this. The line connecting the 2 points, the 2 endpoints of our function on that interval, that line has a slope such that some point along your function is going to have a tangent line that's parallel to it. That's it. That's all we're saying. So somewhere inside of A to B, there's a point C such that, looks like it's about there. I'm not drawing it very well. Let's make that more parallel. There we go. There is a point C within your interval such that the line or a x value C, I should say, there is a value x equal to C such that the line tangent to your function when x is equal to C is parallel to the line that is connecting the 2 endpoints of your function inside of that interval. So you're just saying it's 2 parallel lines of this. That's it. And that kind of seems a little obvious now that it's drawn, right? But it has some implications for us that can let us figure out a lot of seemingly unanswerable questions, like this example here. given that f at 0 is equal to -3, and that the derivative of your function is always less than or equal to 5, how large could f at 2 possibly be? Well, to go about answering this question, the first thing we can notice is that we have an interval from 0 to 2. Okay. And we're going to assume that our function is continuous and differentiable. Well, if that's the case, then we know there exists some c inside of that interval such that the derivative of your function at c is equal to f at b, well, in this case, b is equal to 2, minus f at 0 divided by 2 minus 0, or just 2. Well, we know something else. We know that f prime at c is less than or equal to 5. So this tells us then that f2 minus f at 0, f at 2 minus f at 0 is less than or equal to, multiplying both sides of this inequality by 2, we get that f minus 0 is less than or equal to 10. Now all I'm doing here is I'm focusing in on this part, right? And I'm saying, let's just multiply both sides by 2. Well, given all of this, we also know one other thing. We know that this f at 0 is equal to -3. So this can be rewritten then as f at 2 minus -3 is the same thing as adding 3 is less than or equal to 10. But that tells us then that f at 2 is less than or equal to 7. And we can see that because we can subtract 3 from both sides. So what we've just shown is that the largest that f at 2 can be is 7. And we did that by applying the mean value theorem. So we're assuming in this example here that our function is differentiable and continuous according to the conditions of the mean value theorem, in which case we were able to set up an inequality that let us bound f of 2 from above. Cool. That makes sense. Let's keep moving on. All right, so to wrap things up on this section for this lecture, there's a theorem and what's called a corollary that I want to go over really quick. But before I do that, I want to let y'all know that there is one last problem, or rather in the notes, it's not so much a problem as much as it is an example that comes right after these two. And I want y'all to take a look at it because it's it highlights something that's very important. It highlights a misconception about this theorem that I think y'all should be aware of. So let me go over this theorem and this corollary really quick, and I'll touch on what I'm talking about in the notes in a minute. So this theorem is just telling us that if the derivative of a function is 0 throughout some interval, some open interval from a to b, if that's the case, then your function is just constant on that interval a to b. Now, this corollary, what it says is that if you have two functions whose derivatives are identical on some interval, then those functions at most differ by a constant. In other words, if f prime is equal to g prime on some interval, then the only difference between f and g is a constant. Now, just to make a really quick point about some vocabulary here. One, corollary. Corollary is just an ancillary definition or theorem. It's something that tags along. It's the result of a theorem, or it's another way of saying a theorem. So you could have just as easily said this theorem this way, or this theorem this way. These are two different ways of saying more or less the same thing. They don't say exactly the same thing, but the interplay between them makes them and reduces them to effectively doing or saying the same thing. So that's the difference between, or that's kind of what a corollary is getting at. That's what it's effectively doing, right? Or that's what it means, I should say. Having said that, this example in the notes that comes right after the slide on this theorem and this corollary, it's talking about, or well, rather it's an example of a function that is equal to 0, or well, this function's derivative is equal to 0 everywhere except where x is equal to 0. But the function itself is not constant. And when we look at it in terms of this definition, the reason why is because your first interval is from negative infinity to 0. Your second interval is from 0 to infinity. Your function takes on a constant value from negative infinity to 0 that is different than the constant value from 0 to infinity. So I just want to clarify that example in this theorem a little bit. This theorem does not say that you could remove points off the number line, have a function whose derivative is almost always 0, and still end up with a function that changes a little bit. That's confusing, I know, but when you look at this example in the notes, it will clarify it a great deal. Yeah, having said all of that, I will let y'all go for the day. If y'all have any questions, by all means, please shoot me an email, drop me a line. I'll be happy to help. Have a good one, everybody.